All right. So basically, I know some of these ideas you should be having them already. What is hydraulic fracturing and all of that? So we know that definitely it is a means of
Yeah,
stimulating the well, and you have to inject fluid into the
yeah,
reservoir above its fracture pressure, right?
yes,
So that the
yes,
material definitely
yes,
has a strength, right? For you to be able to
yes.
break that material, you should be able to inject fluid at a pressure that is higher than the fracture pressure of that reservoir. The fracture
Of that
pressure is the
material. Yeah.
maximum pressure above the reservoir becomes fractured. That is it.
Mm-hmm.
So, and this analyzing the fracture pressure of the reservoir is an important aspect because we have to look at a little bit of reservoir geomechanics. It's important
Yes.
in this hydraulic fracturing and even in drilling, because in drilling you have to
Mm-hmm.
analyze the strength of the rock so that you know that whatever the pressure of the drilling fluid is, it should not be above the fracture pressure, otherwise it's going to fracture the reservoir. So you know that there are
Mm-hmm.
two things that are involved during the drilling process. The pressure of the drilling mud should be higher than the pore pressure, because
Yeah.
you don't want the reservoir
Yeah,
fluid
and the
to
pore
get
pressure.
into the formation. Because once it is higher than the
Mm-hmm.
pore pressure, it blocks the reservoir fluid from getting into the formation. And that drilling mud pressure also should be less than the fracture pressure. So the drilling mud pressure is in between two things. It should be greater than the pore pressure and less than the fracture pressure, so that
Pressure.
on the left
Mm-hmm.
side, it doesn't allow fluid to get into the reservoir. On the right side, it doesn't fracture the formation.
Mm-hmm.
So analyzing the fracture pressure of the reservoir is another important aspect that we have to also probably just peep at, not really actually really treating it, because geomechanics is another very huge concept on its own. That would have been another good area also for someone to write a project on. If you have anyone who
Yeah.
probably does not have a topic up to now, you can propose that to the person. If the person is willing,
Okay,
then we
sir.
can work on
Okay.
it. We can use probably TEDLOG, Schlumberger TEDLOG, to do geochemical analysis. All right.
Yeah.
So
Yeah.
generally, when you perform that fracture, it looks like this. There are various models that we are going to explain. We have this on the left here, where we have the geometry of the PKN model. This is a one type of model. There's another type of model which we are going to discuss. But generally, this is how the fracture looks like. You are supposed to understand these various concepts about the fracture. You have the fracture half length, which we denote as XF. You have the width. I indicated this so that you should understand exactly what the width of the fracture is. This is the width of the fracture. Then you also have the height of the fracture. So there are three parameters that defines a fracture. We have the fracture half length, which is a distance from the borehole to the end of the
Yeah.
fracture. That's the
Yeah.
distance. If you look at this, this is what we call the fracture half length. The distance from the borehole,
Yeah.
from the center of the borehole to where the fracture ends. That's where we have the fracture half length. Then we have the width of the fracture, and then we also have the height of the fracture. Because if we don't show it in 3D like this, it may be difficult for you to understand how the width is and how the height is. They may be indicating
Yeah.
that you're confused between the width and the height. All right. So this is another clearer picture of it. This is a one-dimensional model of how it may look like.
Mm-hmm.
We have the
Yeah.
fracture half length, and then this is a three-dimensional picture.
Half length.
It shows you exactly the width from this point to this point. It gives you the fracture half length, and it also indicates to you the height.
The height.
Now, the
Mm.
how and what type of fracturing can we always apply, or what are the various stimulation that we may have within a reservoir? You may also know that there are some cases where the reservoir permeability may be very high, but the area around the wellbore must have been damaged. For example, you might look at
Yeah.
how I explained the concept of skin in that particular presentation that you just watched,
Is it?
right?
Yeah.
That
Yes. Yes, sir.
particular
Yes, sir.
aspect of skin is what you have to note it well. If you have to rewatch it and note
Mm-hmm.
the key points there, you have to note. There are some situations where we have, you know, that there are basically two types of reservoirs. We have conventional reservoirs and we have unconventional reservoirs,
None. Yes.
right?
Yes.
Conventional
Yes, sir.
reservoirs are where we are tapping it for our normal porous and permeable reservoir like sandstone and limestone.
Yeah.
Then the
Yeah.
unconventional is maybe from shale, right? That's where we talk about
Mm-hmm.
reservoir that has a very low permeability. The reservoir has a low permeability. These other reservoirs have high permeability, but the area around the well bore has been damaged. That's the reason why you are doing hydraulic fracturing. So if you have
Fracturing.
a very low permeable reservoir like the unconventional reservoir, where we are dealing with the reservoir that is made up of shield, or where it's made up of shield, then there are various ways in which you can do hydraulic fracturing, because in that particular case, the fracturing has to go very deep into the formation before you can actually get a lot. But now, if we have a reservoir where it is conventional like carbonate and limestone, but the permeability is very, very low, if it's carbonate, it depends on the solubility of the carbonate rock. The solubility of the
Mm-hmm.
carbonate rock is going to determine exactly what type of method you have to use to stimulate the reservoir. If the solubility is greater than 80%, then we can use matrix oxidizing, right?
Mm-hmm.
It
Mm-hmm.
was a matrix oxidizing, right? Injecting acid into the
Yes, sir.
formation to
Yeah,
remove
injecting. Yeah,
yes, to remove the damage. So if the
the damage.
solubility is greater than 70, let's say between 70 and 80, you can use acid
Mm-hmm.
fracking. Acid fracking is when you're using an acid to treat the formation, but you are injecting it at a pressure that is higher than the fracture pressure, so that it
And
is
the
doing
fracture
two things
pressure.
at the same time. It is doing two things at the same time. It is fracturing the formation
Yeah,
and it is also treating the formation.
the
In that
damage. Yeah.
particular
Mm-hmm.
case, you don't use a propant. You don't use a propant. You just fracture it
Yeah.
and leave it like that. You don't use a propant. But if the
Okay,
solubility
sir.
is less than 70%, you now use what we now do a propant frac, right? Where you have to frac
Yes.
it and
Yes.
then you now inject a propant within the pore spaces
Yeah.
so that it now keeps the pore open.
Open.
So
Yeah.
yeah, but for a sandstone, the best possible way is a propant frac for a very low permeable, for a low permeable reservoirs. If the reservoir is a little
Mm-hmm.
having a little bit higher permeability, for carbonate reservoir we can do matrix acidizing. For sandstone we can
Yeah.
do matrix acidizing also. This also, the steep screen out is a recent method of and more advanced method of hydraulic fracturing, which we cannot go into it because it's really more advanced. You have to understand this basic concept before you can even get into this, because the recent methods are more advanced. Now, what are the
Yeah.
various reasons why you may do hydraulic fracturing? Because you may just feel that no, they are doing hydraulic fracturing just probably to 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 treat a damage. It may not be damage. There may be several reasons why a company may decide to probably carry out hydraulic fracturing. It may be to bypass near wellbore storage. Bypassing a near wellbore storage means that you are not treating the near wellbore storage. You are not treating it. What you are doing is you are just creating a fracture that enables fluid to pass, but this damage is still there present, because treating it simply means you remove the damage. What acid treatment will do is
Yeah.
that acid treatment will completely wipe the material that is causing that damage around the well ball.
Yes.
So it has actually treated the damage. Fluid can flow in any direction. But hydraulic fracturing will not treat the damage, but it will bypass it. Bypassing it means that you're creating a path where fluid can flow, but the damage is still there. So
Yeah.
that's the meaning of bypassing the damage. Another
Mm-hmm.
company may do hydraulic fracturing just by to increase the drainage area. You want to increase the drainage area, then they might carry out hydraulic fracturing, or they change the flow regime. Changing the flow regime may
Mm-hmm.
be you have a situation like this. This is a radial flow, right? Where fluids may be
Yeah.
coming from different direction.
From
Generally,
different
when the
direction.
fluid gets very close for a radial flow, when the fluid gets very close to the well ball, the pressure drops. The pressure drops. So you may have
Yeah.
a situation where this pressure drops does not give us sufficient flow into the well ball. The company may decide
Mm-hmm.
now to produce now a fracking system. where the fracking system is now changing it from a radial flow to what we call the bilinear flow. The bilinear flow simply means we have two types of flow. We have the first type of flow, which is from the reservoir into the frac, into the fracking that has been
The
produced.
fracture.
The fracture that has been
Yes.
produced. Yeah, that's the word that just slipped my mind. Into the fracture that has been produced. Then the next flow now is from the fracture into the well ball. This linear flow from the fracture to the well ball now has very little pressure drop, so you can have sufficient flow into the well ball. So that's the reason why we can call it bilinear flow. So the company might do the hydraulic fracturing, and their objective is not to treat any damage, but to change the flow regime. Another company may be to connect natural fractures. You have natural fractures within the reservoir. These are natural fractures that are flowing, that are within the reservoir. We have highly fractured reservoir, and probably there is little means for the fluid to easily flow into the well ball. So what the company will do now is to produce a fracture around this area. When they produce a fracture around this area, it provides a means for the fluid to flow from the fracture into this other major fracture that has been created, and from this fracture in to the borehole. You may also have a situation where you have reservoirs that are not interconnected. You may have maybe lenses of sandstone within a particular shale bed. You may have different lenses of sandstone. So they don't want to go and start drilling different wells in different localities to target each of those lenses. So they may drill a particular well, and they produce the fracking in such a way that it connects all those small lenses of reservoirs, so that all their fluid can flow within a particular reservoir. And that then you may have to connect very thin layers. You may have thin layers that probably contain sufficient amount of hydrocarbon, instead of probably maybe producing perforations in different thin layers. They may just produce a hydraulic fracturing around that area that connect this thin layer from this one and this one, so that all of them now can easily flow into that fracture, and then you now have a single perforation. Then you can also do that to reduce sand production. Sand production is when during drawdown, as fluid is flowing within the reservoir into the borehole. At times, if the flow rate is very high, it carries sand particles together with it into the well ball, and definitely that sand particles can actually destroy some of those equipment, some of those downhole equipment, and all of that. So the company always tries as much as possible to reduce the amount of sand that is produced. So there's one method which we call fracking, that you have to inject a material into the reservoir that is a permeable material, but the essence of this material is to reduce the amount of sand that is produced. So that one is done purposely to reduce sand production. So there are various reasons why a company may carry out hydraulic fracturing, but generally our focus may just be around this particular area. To simplify our study, our focus will mainly be around this particular area. So I've already explained the change of flow regime. All right, so we have talked about damage. Generally, I have mentioned that for a radial flow, as the flow moves from the reservoir towards the well ball, you realize that there is a drop in pressure, right? As you're moving towards the well ball. That's the reason why the company may decide to maybe change the flow regime. So this is a pressure profile as you move from the reservoir into the well ball. This is generally the pressure profile. But you realize that the company may have understood or may have done previous study, and then they know for sure that this is the pressure profile. And at one point in time, because generally along the line, they have to probably stop production, and then they have to test the well to know how the property of the reservoir is, how the property of the reservoir must have been affected by production and all of that. That's where they now have to do pressure transfer analysis, where we talk of well test analysis. So this is the pressure profile, and they may now carry out the pressure transfer analysis, and they realize that the pressure has dropped. There is some kind of a shift in the pressure profile. That means there is an extra drop in pressure as the fluid is moving, as the fluid comes towards the well ball towards the well ball, right? as the fluid is moving from the reservoir, as this area that is very close to the well bore, you have some kind of an extra pressure drop. That extra pressure drop now is coming from the damage, this damage region around the well bore. So this damage, the effect of that now is what generally we call a skin. We are not saying that you call this area skin. No, it's the effect. That extra effect of the pressure drop due to that damage is what we call the skin. So you realize that this particular area must have been damaged. If you go through the video also, you will see some of the reasons, some of the causes of skin. What are some of those things that can cause the skin effect? If you go to the video, you also pick some of those things. So this is maybe one of the most probable reason why a company may decide to do hydraulic fracturing in a sandstone or a limestone reservoir. So you realize that they may now produce a frac, and this frac now is doing what? Bypassing the damage and providing conduit, providing a pathway for fluid to flow easily. So this is more or less a bilinear flow. So at this particular stage, it's no longer radial, but it's more or less bilinear flow. So the company now comes in, and then when they produce the hydraulic fracturing now, the pressure around this particular zone now automatically increases beyond the original, the level that naturally it would have been. So it is now giving us an extra advantage because that area becomes more and more porous. So the pressure profile now has moved above that level. So at this level now, we are having what we call a positive skin. So a positive skin is due to damage, while a negative skin is due to stimulation. That's hydraulic fracturing. So we have positive skin that is due to damage, and then we have a negative skin where there is an upward shift in the pressure profile, and this one is mostly due to what? Stimulation. All right, so there's one important criteria that we have to talk about when we are talking of hydraulic fracturing, which is what we call fracture conductivity. Most of these parameters are parameters that we have already explained, and when you model the fracture, you definitely determine these parameters. We have the reservoir permeability, that's the reservoir permeability. We have the fracture half length. We have the width of the fracture, and then we have the permeability of the fracture. That's the fracture permeability. If you do all of this calculation, generally is going to give us what we call the fracture conductivity. So if you look at what we have here, this parameter that we have down here, which is KXV, is what we call the reservoir flow capacity. And then this parameter up here is what we call the fracture conductivity, is what we call the fracture flow capacity. Let me put it that way. Not the fracture conductivity, is the fracture flow capacity. So
because the fracture conductivity is CFG.
Yeah, definitely. All right.
Yeah.
Oh, I've forgotten that I've not activated Zoom. Anyway, if it goes up, I'll send another link. I was supposed to pay for do the payment to extend. All right. So the essence is that it is an advantage to the company for the fact that if the amount of fluid that gets into the fracture, that same amount of fluid should get out of the fracture into the well bore. So it is ideally the one that this particular value should be 1. In that case, it means that the amount of fluid that leaves the reservoir into the fracture, that same amount of fluid is leaving the fracture into the well bore. But if the amount of fluid that leaves the reservoir into the fracture is, if that leaves the reservoir into the fracture is more than what leaves the fracture into the well bore, it means that fluid is being retained around this particular area. It means that the fracture is not conductive. That's the reason why we are talking of fracture conductivity. It means that probably the exercise was not done well, so the fracture is not really conductive as probably they wanted it to be. So they want this particular value to be close to 1, but generally it can never be exactly 1. It can either be, well, close to 1 means you could be having something like 0.9, maybe 0.8 something or something like that. But it should not be something, it cannot be something like that. Let me say it should not be, it cannot be in a natural life. It cannot be something like 1. Are you okay with that?
Mm-hmm.
All right. So
Yeah.
generally,
Yeah.
as we were talking yesterday, you mentioned something. We're talking about Darcy's law and all of that. The same principle that
Yeah.
controls the flow of fluid in a
Mm-hmm.
natural situation is the same principle that controls the flow of fluid in a fracture situation. The only difference here
Mm-hmm.
is that we are now talking of what? We are talking of the skin effect that comes in. The skin
Yeah.
effect, which in this case is going to be negative, since we are talking of hydraulic fracturing, right? Because
Yes. Yes. That's
after the
true.
hydraulic fracturing, you must determine the skin before you can determine the productivity. If you don't determine the skin, there is no way you can determine the productivity of that particular reservoir.
I see. I
So
see.
that is the first thing that you have to do. We already know that the skin is going to be the negative, because generally a
Yeah.
positive skin is due to damage and a negative skin is due to
Yeah.
hydraulic fracturing. So our
Stimulation.
one of
Yes.
your main objective will be to determine the effect of the hydraulic fracturing by obtaining the skin. What effects has that hydraulic fracturing done on the reservoir? And that can easily be obtained by measuring the skin.
The
The
skin.
higher the
Mm-hmm.
skin, the better the hydraulic fracturing activity that must have taken place. So this is going
Okay.
to be the same equation that we are going to use. We can also calculate what we call fold of increased by taking the productivity index. Productivity index is flow rate per change in pressure. I think I explained it very well
Mm-hmm.
also in that particular
Yeah. In the video.
exercise. So I take the
Yes.
productivity index, J, the productivity index of the natural case divided by the productivity index of the fracture case. If I take it like that,
Yeah.
I have this particular relation, which we call the fold of increase. All
Increase.
right.
Mm-hmm.
Yeah. So generally, how do we obtain the skin? This is a graph that has been, I think, I'll have to check, because you cannot put this graph in your work without indicating who developed this graph. While I'm
Yeah.
checking, you also check to see who developed this graph. So this is a
Okay.
well-established graph that has been designed already, that you can use to determine the skin after the hydraulic fracturing. The x-axis is the fracture conductivity. They may have used a different symbol here, but it's the same thing, right?
Yeah.
They
Yeah.
may have used a different symbol here, but it's the same thing. That's the formula that we have
Yeah.
already seen. So this x-axis
Yes.
is the fracture conductivity, and the y-axis is SF. That means is the y-axis is this parameter. Is this parameter here? This
Yeah.
parameter
Just.
below here.
Yeah.
That's what
Okay.
we have at the
Yes.
y-axis. But this with this RE is not the reservoir radius, but it is the fracture half length. That's the fracture half length that we have there. Is a fracture half length,
Okay.
because we are analyzing it from the reservoir to the end of the fracture. So it represents the reservoir radius at that point.
Yes. That's
So
true.
you
That's
realize
true.
that this axis is linear. This here is linear, but this particular one is what? Is logarithmic. This is a logarithmic scale, but
Yes.
this is a linear scale. So for
Yes.
you to analyze, to determine the skin, you have to first of all start by calculating. You have to first of all start by calculating the fracture conductivity. There's an exercise here that I just indicated. This is a parameter. You calculate the fracture conductivity. From the fracture conductivity, which is 1.698, I will come here where 1.698 is, right? I estimate where
Yeah.
1.698 is. Are you seeing?
Yeah. Yeah. It is six point
Oh,
nine eight
sorry.
per nine four
Oh,
per,
six.
per.
Yeah, yeah, sorry, six. Yeah.
Yeah.
All right.
Mm-hmm.
Yeah, six. So 6 point, the 6 point could be somewhere around here, like this, right?
Yes.
It could be
Yes.
somewhere
Yes.
there. Then you take it up.
Yes, sir.
Wherever you meet this curve, you take it to this direction, and then you read this value.
Yeah.
You read this value. So
Yes.
it means that this particular parameter is equal to whatever value that you're going to read. It's equal to whatever value you are going to read. You already know the fracture half
Okay.
length. You already know the radius of the wear ball. So the only unknown in
Yeah.
this particular formula is what? Right? So the skin has been
Yes.
calculated
That's
in this
true.
case, and it is negative 5.8. 5. So it has to be negative.
5.
If it's not negative, then there's a problem. It has to be negative. Are we okay with that?
Yeah, I see. I
So
see.
this
Yes, sir.
is,
I see.
and this is how we determine the skin. So this is supposed to be part of your methodology. This particular curve is going to be there, but you have to check who produces particular curve, right? Because
Yes,
you
sir.
cannot just
Yes,
put a
sir.
curve like that without saying exactly where the curve is coming from. But I'm not saying
Coming
that you go
from.
and you
Yeah.
do all this calculation, but you are supposed to explain how it's going to be part of your methodology, to explain how you use this
Yeah.
particular curve to determine the skin. And then from there now, you
Yeah.
also have to indicate this particular formula, that this is the formula that is going to use now to determine the flow capacity of the reservoir after the formation, after the hydraulic fracturing.
Fracturing. Yeah.
Yes. All right. You can also, if you like, you can also talk about the fold of increase. I mean, you should talk about it, not if you like. You should be able to talk about it to determine the fold of increase. All
Increase.
right. So we may have two types of situation in a low permeable reservoir. What we may have to do is, like in the situation where we may have the unconventional reservoir, like in a shale, they might produce a hydraulic
Yeah.
fracturing that goes very far into the formation, because the reservoir is very low, having low permeability. They want a situation
Yeah.
where the fracture can access a larger part of the reservoir. But for a highly
Yeah.
permeable reservoir, the essence may just be to treat the area around the well ball, so there is no need producing a fracture that
Yeah.
goes very deep into the formation. So your hydraulic fracture also should have, I mean, you should have this indication there. Are you treating a damage or what? Because the model also will have to be produced also based on that. If you are if you are
Yeah.
treating a damage, or you are producing a fracturing for a low permeable reservoir. Are we okay with that?
Yes. Yes, sir.
All right.
Yes, sir. I'm okay, sir.
All right. So that's just a brief introduction that I just wanted to give you.
Wow. 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 Yes, sir. Okay.